Hello everyone, I'm Hanzhe Tan. I'm happy to share our work, LLM4Decompile, decompiling binary code with large language models. In this project, we focus on decompiled binary back to source code using large language models. I'd like to share some achievements for this project. We are the first open source LLM trained for decompilation, ranging from 1 billion to 33 billion model size. We get 3.1 thousand stars on GitHub and rank as top 3 GitHub training report on March 18th. Our decompilation result far exceeds GPT-4 for over 200%. So let's begin the journey. I'll briefly present some background on compilation and decompilation, then introduce our method, followed by the experimental results. Finally, I'll discuss the challenges we meet. What is compilation? Given a source code like C or C++, the compiler GCC will convert the source code to a machine-readable binary of zeros and ones. Let's look inside. The source file will be first preprocessed, then analyzed its syntax, semantics to compile into assembly code. Then the assembly will be translated to the binary. Note that the binary now is not executable. It needs to be linked with the library like the stdio.h to make it executable. The executable is something like the file exe extensions in the Windows. Here example for the compilation. gcc-o hello.exe hello.c. So after compilation, we get the hello.exe and it can be directly run in the system by clicking it. Note that you need to compile the C for different systems like Mac OS, Linux, Windows. While in AI community, we researchers prefer Python. The language works different from the C. We first need to have a Python interpreter. For example, the apt install Python to get this environment. Then use the Python environment to run the Python code, like Python hello.py. So do not need to compile the Python code for different systems. The interpreter will do the job. And the compiled language like C or C++ has the benefits that in most cases, it will run faster and much faster than interpreted language like Python, as we have done all the interpreted job during the compilation because we convert the C into a binary. So in the contrary, if you want to understand the source code directly from the binary, it will be very hard. That's why we have this project to unlock the binary and show the source code. So here's the decompilation. Convert binary back to source code. Note that binary are 0 and 1s. No LLM can directly read the 0 and 1s. So we need to first convert the binary into assembly code, which is deterministic. The conversion from binary to assembly is governed by some rule, and binary and assembly are in fact equivalent. We treat the concept of assembly and binary as the same. In fact, there are few decompilation tools. For example, Ghidra, open source decompilation tool developed by the United States National Security Agency. Here's an example to compile and decompile. First, the source code is compiled to a binary, the 0 and 1s. Then disassemble to the assembly language, which are some machine-level operations like push the stack, move the value. Then the assembly is decompiled by Ghidra into a pseudocode. As we can see, the pseudocode largely follows the logic, but extremely hard to read and understand. It produces the undefined type and converts the for loop into an uninterrupted do while inside another while. The simple structural comparison is converted into the complicated polynomial arithmetic. So we want a tool which can decompile the binary into a correct and easy to understand source code. Here's a simple demo on the LLM. I think we are all the expert on LLM. It generates the output with the probability based on the previous input. There exists several work on LLM4Decompile. We can group them into two categories. One is end-to-end, which takes the assembly as input and directly decompile it to the source code, like the BTC, Slate, and Nova. However, they're with small size. But we know in the human-readable leaderboard, we can see larger models have significant improvement over smaller counterparts. Scaling up the model is very impressive, so we want to develop the first open-source LLM4Decompile series with model size ranging from 1B to 33B. Another category is refined pseudocode from some decompilation tools, like the DGGPT, DCGPT. But in the training data, most of the open-source LLMs, they are not trained with much binary or decompilation data, thus their capability to decompile is not well established. So here's our work, LLM4Decompile. It works both directly on the assembly and refine the decompilation results from Ghidra. The framework is straightforward. For source code, we first compile it to a binary and get disassembly or pseudocode. Then we train LLM4Decompile to generate the source code, calculate loss between the generation and ground truth. Let's discuss the LLM4Decompile from assembly first. We name it as LLM4Decompile end. As we have discussed the compilation process, to get the training data, we need to compile the source code to a binary. However, it's hard to get executable, as it requires a complete dependency and specific environment to compile. We only get 400,000 from it. It's much easier to get an object file which is not linked. We can get 4 million, 10 times the size of real executable data. These two completely are quite similar to each other. Therefore, we can use the large compilable but not linkable data as the first training stage, then use the executable data to further tune the model to make it practical in real world. We also use different optimization states to expand the data, as these flags are frequently employed in real projects. Here's an example for the compilable but non-linkable data from EXE-Bench, the training dataset of a project. We can see that we fix the dependency and of the type defines external functions to fool the compiler, so we can compile the data. As these definitions are crafted, the compiled result cannot be linked to real definition and thus not executable. Let's compare the non-linked, only compiled data and the linked executable data. We can see they're almost the same, but only difference is the function cross-referenced. In the linked executable version, the jump is to a real address 25710 of a function memory set, but in the unlinked only compilable version, it's only an offset 50 from the function start address and does not have any meaning. So we can utilize the large only compilable data to ground the LM with decompilation knowledge, and use the executable data to make the model useful in real practice. So our method is straightforward. Compile the data, go for the training. The main challenge lies in the engineering part. We iterated for over 50 versions and got the final results. In total, it took around 8-card A100 workstation running for over 1 year. For the evaluation, we converted human-eval Python solutions and assertions to C, namely as human-eval decompile test on 4 optimization stage, in total 164 times 4 samples. The dataset contains only one function, no user-defined types of structures or functions. We also used the EXE-Bench test set, which are real codes from GitHub with lots of user-defined structure functions. In total, there's 2021 samples, each with 4 optimization. To evaluate, we used the re-executability. After decompiled code, we integrated it with the original assertions. If the decompiled code can pass all the assertions, then the decompilation is successful or re-executable. So here's the main result for LLM4Decompile, which decompiled the assembly code to the source code directory. Our model is based on DeepSeek, which the original model does not have the capability to decompile. While GPT is really powerful, on human eval, it can decompile 16% of code, while our 1.3 billion model can easily outperform the GPT, with 27 decompilation success rate on human eval and 40% on EXE-Bench. The 6.7 billion model significantly bypasses the 1.3 billion one, with 45% on human eval and 18% on EXE-Bench. Note that the 1.3 and 6 billion model are trained for 15 billion tokens, while the 33 billion model are only trained for 200 million tokens due to the compilation limitation. But with only 200 million tokens, the 33B still outperforms the 1.3B model, reaffirming the scaling law and the value to scale up the model size. The ablation also shows the importance of the two-stage training. Let's discuss the LLM4Decompile refine, which refines the result of Gidra pseudocode, but limited by the decompilation speed of Gidra, we only generate 400,000 functions times 4 optimization data, which is around 1 billion tokens. Here's the results. Note that the Gidra is a powerful decompilation tool. It can successfully decompile 20% of human-eval data, which is refined from GPT-4o, where we use GPT-4o to refine the results of Gidra decompiled pseudocode. The decompilation results significantly raised to 35%. With training, our LLM4Decompile refined 1.3B significant bypass GPT-4o, and our best model, LLM4Decompile refined 22B based on CodeStraw, achieves average of 64 re-executability rate, almost 2 times over GPT-4o. We also provide ablations on the training apples and model size. We notice that large apple of training is not always beneficial, but an apple of training is strong baseline. With longer apples, the training starts to overfit and lead to poor performance. As for the size, it can be noticed that 6B model achieves comparable performance with the 1B model with only 20% of data, and the 33B model reaches similar outcomes to 6B model, which is 10% of data. Also, these ratios may differ with varied datasets. Scaling up the size and data is really beneficial. Here's some samples decompilation results from different methods. GPT-4o output is plausible, yet failed to recover the array dimension. Gidra's pseudocode is very hard to read. GPT refined Gidra result marginally enhanced the readability, but fails to recover and render for loops and array indexing. Conversely, LLM4Decompile and output from refined produce accurate and easy to read outputs. Finally, we discuss the challenge for the project and talk about the future directions. First, our LLM4Decompile can only do the decompilation, but engineers want something like a chatbot, a GPT which is good at reverse engineering. So we plan to support instructions and allow users to provide contents. And our overall model now only supports for x64 Linux, while we receive lots of issues asking for supporting multi-language platforms and architectures, which we are working on them. That's all for the LL4Decompile. Thank you.